Good afternoon, guys. I apologize for not being in class today, but I think this will do. The poetry slam kind of put a wrinkle into how I was planning on getting you guys the content for 10.3 using calculus with parametric equations. So essentially, when we have two equations like this parametric equation, this set of parametric equations, how do we find the derivative dy dx when what we have are equations written in terms of t? So what's worth figuring out here is essentially we have dy dx, and unfortunately when I say take the derivative of one of these equations, for instance, let's say if I look at this one down here, like to take the derivative of both sides there, I would end up with a dx dt, since this equation is written in terms of t. It's a function of x in terms of t. So we could go ahead and say dx dt is cosine t, and that would be fine. But that doesn't really help me find dy dx, or does it? So essentially, what we can do is kind of recognize that what if I took this whole fraction of dy, if I took dy dx and I multiplied it by 1 over dt, both the top and the bottom by 1 over dt, now what I would have is dy dt over dx dt. So essentially, if I want to find the derivative, dy dx, so the derivative of y with respect to x, but my equations are functions of t, we're essentially going to do the derivative of the y's on the top, the derivative of the x equation on the bottom. So for instance, so we already found dx dt. If I look at this, I could say dy dt would be the derivative of cosine t is negative sine t. And so dy dx is going to be dy dt, negative sine t, over dx dt, cosine t. So dy dx is negative tangent of t. And so now we have, just like our original equations, our parametric equations were x and y in terms of t, now we have a derivative of x and y in terms of t. So then what happens is, how do you take second derivatives and or third derivatives? So when you think about finding the second derivative, you're essentially taking the derivative of the first derivative. So on top, we're going to take d dt of dy dx, our first derivative, which will be in terms of t at that point, over dx dt, which we will have already found as well. So let's look at an example. Okay. So essentially, we're asked to find the slope and the concavity of this set of parametric equations, given that at the point 2, 3. So to find the slope, we're going to find dy dt, which is going to be, we're going to take the derivative of that first equation of dy. So dy dt, we'll have the 1/4 out front times 2t, which is just going to be t over 2. And dx dt, well, this is really t to the 1/2. We could call that 1/2 t to the negative 1/2. So to find dy dt, to find dy dx, my bad, we're going to take t over 2 divided by 1/2 t to the negative 1/2. And so there's a couple of, I might say both of these are over 2, so those will cancel. And then I have a t on top and a t to the negative 1/2 on the bottom. So with a little bit of work here, we can get that dy dx equals t to the 3/2. All right, so from there, if we want to take that second derivative, what we're going to do is take the derivative of t to the 3/2 with respect to x, which is essentially, it's almost like I'm going to take that d dx and turn it into d dx dt. And then, so now I'm taking the derivative of t to the 3/2 with respect to dx dt. So this is starting to look kind of fancy. Might be worth noting that the derivative of t to the 3/2 would be 3/2 t to the 1/2 over dx dt. We already found dx dt. It is 1 over 2 t to the negative 1/2. And now with just a little bit of simplification, we can see that this simplifies down to 3t. All right, so we have our first derivative is t to the 3/2. Our second derivative is 3t. We have one more problem here that we haven't really addressed, and that is, well, what do we normally do to find slope? We plug our point here into our derivative. Now, when I look at this point is in terms of x and y, not in terms of t. So the last thing we kind of need to think through is, what is t? And it turns out that this seems slightly complicated, but it doesn't have to be. We basically are saying, I'm going to use this equation. You could use either one of these, and you pick the one that is more pleasant to solve. So if I gave you, well, I know that x is 2 equals the square root of t. I get t equals 4, okay? Or if I wanted to, I could say, well, I know the value for y is 3. And we do some basic algebra here. We're going to get 12 equals t squared minus 4, and essentially we're going to get t equals 4 either way. So essentially, I know that for this, in order to be at the point 2, 3, my t would have to be 4. Okay, so you can use the point to help you figure out which value of t you're plugging into your derivative. So now finding the slope just means I need to evaluate dy dx evaluated at t equals 4. Well, that's going to equal, let's see, 4 to the 3/2, which is 8. So at the point 2, 3, the slope of the tangent line is 8. And likewise, to find whether the concavity is concave up or concave down, a reminder, we look at the second derivative to do concavity. And if I plug 4 in for here, it becomes 3 times 4. And so 12. Which we don't really care about the number, but we do love that 12 is greater than 0, so that we can say that this is concave up. All right. So for this next one, guys, you're going to go ahead, throw this in your calculator real quick. I'll give you a second. And when you throw this in your calculator, I would anticipate a graph that looks kind of like this. It even has a specific name. This one is called a prolate cycloid. And it's kind of an interesting graph, but it should look something kind of like this. and here's the point 0.02. And so as we look at this graph, and I'll give you guys another second if you haven't gotten there yet, but as you look at this graph, there are essentially two tangent lines here. We have the one going this way and the one going this way. And so now that we're dealing with parametric equations, we could have more than, instead of just functions, we could have more than one tangent line to a given graph. So let's find the equations of those two tangent lines. All right, so the first thing we would need to do to find the tangent lines is find the derivative. So we're going to find dy dx, which means we've got to find dy dt, which looks to be pi times sine of t. And so that'll be the numerator of my dy dx, pi sine t. And dx dt would be 2 minus pi cosine t. That's t. All right. So now that we've done this, we can, it feels like we should be able to just plug in to find the slope. We kind of can, but not really. So, because first we have to figure out what value of t gets us to the point 0.02. So we basically have two options. We can plug 0 in for x, or we can plug 2 in for y. And basically, both of these would give us the same result. It turns out that solving this one in the left is yucky. We can try, but it's kind of weird. It ends up being, I keep writing sine pi, I mean sine t. It ends up being just kind of a pain in the butt, whereas if we look at, say, this one, we get 0 equals negative pi cosine t by moving that 2 over. And then, so 0 equals cosine of t. So where does the cosine of t equal 0 when you think about your unit circle? Well, cosine equals 0 when x is 0, so essentially up here and up here, or down here. So t is essentially plus or minus pi over 2. The angles on those angles on the unit circle. And so, so now that we know that, the reason we have two tangent lines is that we have two different values for t that give us that slope that we can plug in to find that, or that give us the point 0.02. So because we hit 0t or 0.2 twice, we get two tangent lines, essentially, is what's going on here. So, so let's go ahead and find the value when we plug in pi over 2, or to find the value of our slope. All right, so let's go ahead and plug pi over 2 into in for t. So we're going to get pi times the sine of pi over 2 over 2 minus pi times the cosine of pi over 2. All right, so in my numerator, the sine of pi over 2 is 1. So this, I just have pi. And in my denominator, the cosine of pi over 2 is 0, so pi times 0 is 0, so I end up with pi over 2. Now, if I plug in the negative pi over 2, what'll happen is, well, let's just do it real quick. The only thing that's going to change is the sign of the numerator, okay? So as we go to find the equation, we've done all the hard work now. We just need to find the equations of our tangent lines. if we do point slope form, we would do y minus 2 equals our slope. I'm going to use the first one, pi over 2, times x minus 0, which is just x. So there's my first tangent line. And the only thing that'll change for that is that it'll become negative pi over 2. All right. So way back, we learned in Chapter 7, we learned the arc length formula. My intention for this space of your notes, it was, excuse me guys, my intention for this space in your notes is to write the proof of the formula on the next page as to how you find the arc length of something in parametric form. For the sake of brevity of video and to give you guys a little bit, this is something that with the shortened periods today and all that kind of stuff, I feel a little bit like this is something that could be cut. So I'm going to say remind me to prove later. And I will be happy to show you guys the proof of this. But in reality, we were just going to algebraically manipulate this proof so that we can get to this new arc length formula if we are in parametric. If we have an equation in parametric form. So let's go ahead and find the arc length in this particular scenario. So those A and B are the bounds on T, okay? So the arc length is essentially going to equal the integral of the square root of, so we want to find dx dt, which I get 12t. So that's going to be 12t, and then we square it. And then dy dt, I get 6t squared. And then we got to square that, all dt. And just like before, we're dealing with stuff with arc length and all those kinds of things. At this point, I am completely comfortable with, I'm asking, do you know how to, and we didn't put our bounds here, so the bounds would be from 1 to 4. I am completely comfortable with you guys just using the setup statement. I'm not testing, in this particular case, I'm not trying to figure out, do you know how to do the integral? I just need to know, do you know how to set up the integral? So you can go ahead and throw these in your calculator just as they are. So when I'm doing this, I threw it in my calculator wrong. Hold on. I found S to equal 156.52. So hopefully this is helpful. We can talk about it more if you need to tomorrow.